Hello there. In this video we're going to continue our discussion of non-elementary primitives by looking at a particular problem that is actually really intuitive to understand. So recall that the equation of a circle, so let's assume this is say minus r, and minus r. Let's assume this is a circle anyway, with equation x squared plus y squared is equal to r squared. And we can find that the equation for the top is given by y is equal to the square root of r squared minus x squared. So using our arc length relationship, we can find that the circumference of the circle is going to be equal to 2 times the integral from minus r to r of the square root of 1 plus the derivative of this top half, the square root of r squared minus x squared, the quantity squared, dx. So what we're going to be looking at, and of course you can prove that that is equal to 2 pi r, what we're going to be looking at is the case where these axes here and here are non-equal. In particular, we're going to be looking at equations of ellipses and the arc lengths of them. Alright, so before we get into the main topic of discussion for this video, I just want to review just basic properties of ellipses, just in case one has forgotten. So the Cartesian representation for an ellipse is given by the equation x squared over a squared plus y squared over b squared is equal to 1. So in terms of the graph of an ellipse, let this be x and let this be the y-axis, and let the ellipse be situated around the origin and show. You could always shift it to another center if you want. So the number a is this distance here, and let b be this distance here. Typically we like a to be greater than b. If not, just simply rotate this ellipse around the origin 90 degrees. The circumference will be the same, and that's pretty much what we're going for here, so it doesn't really matter. So we can choose a greater than b without loss of generality throughout this discussion. So I'm just going to rewrite our equation into something a little bit more easier to work with. So we have b squared x squared plus a squared y squared is equal to a squared b squared. So the initial goal is to get a Cartesian function representation for the top side of this ellipse, which we can achieve by solving for y. And then we can multiply that arc length by 2, and that's going to give us the arc length of the ellipse of interest. So I'm just going to solve this equation for y, so I'm going to isolate this term. So this is going to give us a squared y squared is equal to a squared b squared minus b squared x squared. And then I can divide both sides by a squared. And that's going to give us y squared is equal to b squared minus b squared over a squared x squared. And then I can take the principal square root of both sides. And that's going to give us our function of interest. So therefore the function that we're going to be looking at is going to be equal to the square root of b squared minus b squared times x squared over a squared. From here I can factor out the b squared outside of the square root. And that's going to give us the function that we're going to be working with primarily, b times the square root of 1 minus x squared over a squared. So for the arc length representation, we're going to be finding the derivative, so let's just differentiate with respect to x here, which is going to be b divided by 2 times the square root of 1 minus x squared over a squared, and then multiplied by this interior quadratic, which is going to be equal to negative 2x divided by a squared. We clearly see that these 2's will cancel, and then we're going to square both sides of this equation. So the square of the derivative with respect to x is going to be equal to b squared x squared all over 1 minus x squared over a squared times a to the power 4. I'm then going to distribute this a to the fourth into here, and that's going to give us f prime of x squared is equal to b squared x squared all over a to the fourth minus a squared x squared. So from here what I'm going to do is I'm going to factor out an a squared out of this denominator. So this is going to give me f prime of x, the quantity squared, is going to be equal to b squared x squared divided by a squared multiplied by the quantity a squared minus x squared. So what I want to do now is I'm going to divide top and bottom of this equation by a squared. So once I do that, I'm going to divide a squared and x squared into the same quantity. This a squared is going to cancel, and I'm going to distribute that into this expression simultaneously. So once I do that, that's going to give me what? So then we're going to have f prime of x, the quantity squared, is going to be equal to b squared times x over a, the quantity squared, all over a squared times 1 minus x over a, the quantity squared, right? We're going to be using the substitution u to be equal to x over a. So our expression with respect to x is going to be equal to b squared u squared all over a squared times 1 minus u squared. Alright, so now we're ready to find the arc length of our ellipse. Alright, so remember that the arc length is going to be equal to the integral from alpha to beta of the square root of 1 plus dy over dx, the quantity squared, dx. So simply replacing this in this term, we have the arc length is going to be equal to 2 times the integral from minus a to a of the square root of 1 plus b squared u squared all over a squared times 1 minus u squared dx, right? And remember, it's 2 times because we want the top half and the bottom half, and this function is only referring to the top half. Alright, so let's turn this integral totally in terms of du. So remember that u was equal to x over a. So when x is equal to a, we have that u is equal to 1, and when x is equal to negative a, u is equal to minus 1, and du is going to be equal to 1 over a dx, forcing dx to be equal to a du, right? So replacing all these things into our integral, we have that this is equal to L equals 2 times the integral from minus 1 to 1 of the square root of 1 plus b squared u squared all over a squared times 1 minus u squared multiplied by a times the differential of u, right? So we can get a common denominator here. So I'm going to multiply top and bottom of the 1 by a squared 1 minus u squared. So that's going to give us L is equal to 2 times a times the integral from minus 1 to 1 of the square root of a squared 1 minus u squared plus b squared u squared all over a squared times 1 minus u squared du. Alright, so I'm going to factor out this a squared outside the radical and cancel with this a. And I'm also going to distribute this a squared into this parentheses on the inside. So once I do that, I have L is going to be equal to 2 times the integral from minus 1 to 1 of the square root of a squared minus a squared u squared plus b squared u squared all over 1 minus u, the quantity squared, du. And I'm going to rearrange this just a tad bit. I'm going to group these two terms together since they both have u squared. So I'm going to have L is going to be equal to 2 times the integral from minus 1 to 1 of, so I have a squared plus b squared minus a squared times u squared all over 1 minus u squared times du. And then I'm going to factor out a squared out of this term and this term and pull that a out. So that's going to give us L is going to be equal to 2 times a times the integral from minus 1 to 1 of the square root of a squared. I'm going to switch these around. I'm going to instead make it a squared minus b squared because we're assuming a is bigger than b. So we're going to have minus a squared minus b squared all over a squared times u squared all over 1 minus u, the quantity squared, du. Oh, and we factored out that a squared, so therefore that should just be 1. Alright, so now I'm going to just perform a little substitution because this is just a constant. So I'm going to define k squared to be equal to a squared minus b squared all over a squared. Therefore, we have L is going to be equal to 2 times a times the integral from minus 1 to 1 of the square root of 1 minus k squared u squared all over 1 minus u squared du. And also notice that this function here in terms of u is an even function, and we're going over a symmetric integral, so we can rewrite this as the integral from 0 to 1 and multiply by 2, right? So we have L is going to be equal to 4 times a times the integral from 0 to 1, and u is just a dummy variable, so we can switch back to x if we want. And that's just going to be equal to 1 minus k squared times x squared all over 1 minus x squared times dx. And this expression here is what our goal is. So this is what we call an elliptic integral, right? Because once we evaluate this integral, then we get the closed form of the arc length, right? But a property for this integral is that for most k, this integral is non-elementary, which means we cannot express this in terms of exponentials, polynomials, and combinations of each, right? So, therefore, we're going to define a function. So, definition, we're going to define the function ekx. We're going to define this to be equal to the integral from 0 to x of the square root of 1 minus k squared t squared all over the square root of 1 minus t squared dt, right? So this is what we refer to as an elliptic integral. Therefore, the arc length that we were interested in finding before, which was equal to 4a times the integral from 0 to 1 of the square root of 1 minus k squared t squared all over the square root of 1 minus t squared dt, is precisely integral equal to elliptic integral with parameter k evaluated at x is equal to 1, right? So that means the arc length is given by 4a times the elliptic integral evaluated at 1, where k is defined to be equal to the function of a and b as defined before, right? Now, as I said, for most k, this function is non-elementary, but as an example, if a is equal to b is equal to 1, then our ellipse is what shape? In particular, that is going to be our unit circle, right? Which, as we know, the arc length is going to be equal to 2 pi, right? So if a is equal to b is equal to 0, then one can find that the value of k that we have before is going to be equal to 0, right? So that means our arc length is going to be equal to 4 times 1 times the elliptic integral with parameter 0, evaluated at 1, and this is going to be equal to 2 pi, which means we have a particular value for our elliptic integral. Therefore, E01 is going to be equal to pi over 2, so that's a direct result, right? And you should be able to verify that this value here, E01 from 0 to 1, which is equivalent to the square root of 1 minus t squared dt, actually is equal to pi over 2, and you can verify that for yourself. So this is just an introduction to elliptic integrals. In the next video, we're going to be looking at a couple more properties and also do an extensive example of how these are used in just calculating normal definite integrals of elementary functions. Hope you enjoyed.